No, I just do it. Thank you very much for all your kind words and for your invitation. And I'm very happy to see so many young faces here. So, well, he asked me to say something about what we are doing in multiversity. So the idea is that the existing educational system is faulty. And it is premised on a false history. And therefore, we need to re-examine all of it. And this is what we are trying to do. So starting from history and philosophy of science, because that's where it went wrong with Macaulay, and saying that we are immensely superior, the West is immensely superior in terms of science and technology at that time, 1832, 1835. So I think that that's what we are trying to do. And in redoing all the, whether it is history, philosophy of science, mathematics, statistics, philosophy, you just imagine, there's nothing on Indian philosophy really being taught in most of the Western universities. The history, philosophy of science hardly mentions India, and so on. So we want to correct those things. That's what we are trying to do. So maybe I should give that requires a separate talk. It's a very big project. So I'll focus on calculus today, because most of you, I suppose, have come to listen to the calculus. So I want to, basic idea is that I'm trying to debunk, there's a whole lot of glorification that goes on in the Western history of science. And the aim is to debunk it and to tell you what the real stuff is, what really happened. So let me start with something very basic. We'll start with a very elementary arithmetical question. Anybody knows how to do it? Okay, now you don't know Roman numerals. What I want to bring out is something else. Think of the number of symbols that you need to represent a simple number. There's 4 digits here and so many here. So why do you need so many symbols? You see, the story goes that India invented 0. That's not the story. The story is that there was very inefficient arithmetic. And the arithmetic that you do today is Indian arithmetic, and it came here for its efficiency. And 0 is a very small part of it. So that's what I want to do. Now try doing this in Roman numerals. I think the universe might come to an end before you finish, unless you start inventing special symbols and so on, which you can always do. But the point is, such a number didn't arise at all in Roman thought. It exists in Buddhist thought. We find it in the Lalita Sutta. So the idea is that it was used. They were because these large numbers were there, and these large numbers were there because there was a superior decimal place value system. So even in the Yajurveda, you find numbers up to 10 to the power 12. The names are slightly different from the names in current use, and this is what you find in the Lalita Sutta. So there's a chapter in which the Buddha is challenged, and then he starts naming them. And if you have names, then you presumably have uses for that. And of course, you have very large numbers in Jain literature too. So this is the verse from the Yajurveda. You probably won't be able to read it, so I will translate it into simple Devanagari. So the words, many of the names are what they still are, but Arbudam, which is Arab, meaning has changed, and you don't have Kharab, they came later. So the point of the place value system, it's not 0, it's a place value system, led to efficient arithmetic, as in the methods which you learned in school for addition, subtraction, and so on. That's efficient arithmetic. And they were called Patiganit by Brahmagupta and so on in his Brahmasput Siddhant. And it was followed by so many other books, Sridhar, Patiganit, Mahavir, Ganit Sar Sangrah, Bhaskar's Liya was very famous. And these things went to the Beit al-Hikmah, the House of Wisdom in Baghdad. And there, as you know, Al-Khwarizmi wrote Hisab al-Hind. And the word algorithm comes from Al-Khwarizmi's book, Hisab al-Hind. The point, of course, is to keep stressing this. Why was this Indian arithmetic imported? Why was it imported by Arabs, and why was it imported through Arabs into Europe? So it's because of its efficiency. Now let's look at this problem. How about this? Does somebody have any idea how to do it? How long it takes? How difficult is it? Because that's how the Romans used to do it. That's how the Greeks used to do it. And the question that you then have to ask is, if they could not do these elementary arithmetic problems, how could they do all that science they are supposed to have done? It's intrinsically improbable. Alright, now you're not allowed to do, when I give this problem to my students, some of them they quickly convert it to decimals, calculate it with the calculator and then convert it back. That's not it. How did they do it? So they did multiplication by repeated addition. So here's a simpler question. Can you add these two? Well, because they had no place value system, because they used an abacus, you have to think of these as counters and or coins, and then you pull together all the coins for all of them and you simplify out and you get the answer. So it's not a very complicated process, but it's a very tedious process. Just a simple addition takes a long time. And the sum, of course, is 107. It comes out to be that much, but it's a very tedious process, so many steps. So the problem is now if you were to multiply, you have to do this so many times, 29 times. So simple multiplication, which you can probably do in your head, which you can do very easily with algorithms, would take a very, very long time here. That was the problem. So when the Greeks and the Romans did it with an abacus, it was extremely inefficient. But that inefficiency is not trivial because of its implications for the entire history of that Greeks did this, Greeks did that. Everything is based on late texts. That's not reliable evidence. You're inferring something across a span of 1,000 years with no intervening continuity, as exists in the Indian case. So those claims are wrong, and that's what my book is Science Western is about. It's non-textual evidence, like non-textual evidence of the calendar. It's reliable evidence, evidence which you can understand instead of texts, which are very remote, which are manipulated, all sorts of things happen. And they were meant for the purpose of glorification. There's a total discontinuity in time, space, language. So you cannot rely on that. A lot of speculations are built into it, prejudice speculations, and that's what has to be done. And you should also recall that this false history was used to justify racist domination, not just by Kant. It's just a name I have taken. There's so many of them. You'll find the references in Euclid and Jesus, Carlyle, there's so many of them. Hume started it. And it was used to impose colonial domination and exploitation by Macaulay. How did he change the education system? He didn't force it down people's throats. He said, we are superior, we have this, and people got taken in. Raja Rammohan Roy started the Presidency College because he was persuaded. So this is the point I would like to emphasize. The biggest mind-stopping cliche is that history is written by victors. What can you do about it? That's not true. This history was written by losers in a military conflict, and it helped them to gain an empire. So false history has power, great amount of power. Let's not forget it. It's not something, fait accompli, victors did it, and only when you have a military victory you can do it. So therefore it is important to expose these falsehoods, because just as racism has not ended, colonialism has not ended. It goes on, it's very much there, and that's why we are doing it. Alright. So now I want to point out what went wrong. So because it was efficient, it was imported. It was imported in two steps, first from Cordoba in the 10th century, then by Florentine merchants for its advantages for commerce. Now this is the important issue. When it was imported, now this is arithmetic, elementary stuff, people didn't understand it. And this part of the story is suppressed. Whenever new knowledge comes in, people don't understand it. Okay, so this story that people didn't understand is there in the very terms, Arabic numerals and the term 0. So the first import was by Gerbert, who later became Pope Sylvester II. He was a very learned man. He is represented as a black magician in Christian art. He wrote a book on the abacus. But because he wrote such a book, he thought the only way to do arithmetic is through an abacus. So what did he do? When he got these methods, he got an abacus constructed for them. He didn't realize that what's the point of the place value system, and that's why he thought there was some magic in the numerals, the shape of the numerals. You still do arithmetic with abacus? Something in the shape of the numerals. So what was the shape? This is the shape. This is the Pope's abacus from 976. You see, he does recognize something about the place value. There is nothing for a 0 there. So that's not about the symbol or lack of symbol for 0. That's not the issue. The issue is that he constructed an abacus. An abacus is an inefficient way of doing arithmetic. Algorithms are efficient. And he didn't realize that difference. The word 0 itself comes from cipher, mysterious code, cipher, how do you call it? But what's mysterious about it? So the mysterious thing is that if you look at Roman numerals, they are additive. So 12 means x plus I. But that's not the case in place value. 120 doesn't mean 1 plus 2 plus 0. So that's what they said. This is something they complain. What is this mysterious symbol 0 which has no value in itself but adds any amount of value to the preceding number? And that's why they changed their rules for financial contracts. Because you could add zeros, you could not do that with Roman numerals. And so they changed the law in Florence, Florentine law. That's why when you write a check, you fill in the symbols and fill it in words. Because the symbols are not to be trusted. They are these mysterious Arabic symbols. So now what you do with the computer, you have to key it in. If you make a mistake, that's too bad. So they actually came into general circulation only in 1572. Think of it, 600 years. 600 years it took. In fact, it took longer. Actually, the British Parliament burnt down, with that. But I'll tell you that story some other time. The only point I want to say is that when these new techniques were imported, they were not understood in Europe for centuries. Simple arithmetic is what we're talking about. There's a lot more to go. So this is the thing that it is not about just 0, it's about efficient arithmetic. Now if you don't mention that, you're suppressing that there was inefficient arithmetic, and then that has a long story behind it, linked to it. The second thing is that it took a very long time, 6 centuries, for people in Europe to understand this arithmetic and accept it and introduce it in their education system. That was 1572 was Clavius and the Jesuit education curriculum. Story of trigonometry is similar. So trigonometry originated in India, travelled by Arabs, travelled to Arabs. Al-Khwarizmi repeats Aryabhata's value of pi and so on. And then it was imported first via Toledo. Now, Toledo, if you see the translations, Toledo, there was a huge Arabic library. It was captured during the Crusades and it was mass translated into Latin. Around 1125, not around 1125. Now you look at the word sine, you mentioned sine. So it derives from the word jabe. This jabe, pocket. What has sine got to do with pocket? Now that sort of thing should alert you that there is some misunderstanding going on, misunderstanding at work. So, because obviously a pocket has nothing to do with science. So it was a misreading of jabe, was a misreading of jiba. And jiba, which was just written as j and ba, without the nukta system, which was not prevalent at that time. Who was doing the reading? Mozarabs and Jews. Because the translation was not done in one shot. The translator didn't know the mathematics, he didn't know Arabic. Somebody translated into Romance languages, and from Romance languages, the official translator translated into Latin. So it was a big process. He didn't neither understood what was happening. He said, Jaba must be Jab, what else can it be? So that's how you get it. So Jiba was from the Sanskrit Jya or Jiva, which means cord. Now here there is another conceptual misunderstanding. We are not just talking about linguistic errors. Let me come to that. So Amartya Sen has been telling this story recently, and something came in the Hindu, and I wrote a rejoinder. It was not published. But because there is this fact which has been hidden. What is the fact? That this transmission of knowledge was accompanied by misunderstanding. Not just a linguistic misunderstanding, a conceptual misunderstanding. And this is my epistemic test. If you have two students who produce an identical copy, how do you decide who has copied from whom? You ask them questions. And the one who can't answer has copied, because when he copies, even while copying they will make mistakes. So if you find some subtle mistakes here and there, you can be sure this is the guy who has copied from the other guy. So that's the epistemic test. I apply it extensively, including to all those people who have plagiarized my work. So there are a lot of them. So if you look at the word trigonometry, the very word trigonometry indicates a conceptual misunderstanding. Just as 0 indicated, cipher, It is about triangles. Trigonometry is about measurement of triangles. But it's not that. The concepts relate to a circle. You learnt it like a triangle, I'm sure. Opposite side by hypotenuse. Am I right? So it relates to a right angled triangle, but that's wrong. It relates to a circle. So nothing to do with triangle. You should perhaps call it circlemetry. And they are discussed, these concepts are discussed in the chapter on the circle. So this difference is non-trivial because you need to, if you want to do the circle, you have to be able to measure curved lines, not just straight lines. And even to define an angle of 1 degree, it's a non-trivial task. I have a challenge at the end. If somebody is able to do it axiomatically, formally. Remember, Russell and Whitehead took 376 pages to prove 1 plus 1 equal to 2. To define that angle, you need at least 1,000 pages of 1 degree. Because you have to do it formally, not empirically. Empirical is very easy. But empirically, how do you do it? If you take the geometry box today with which you learn geometry, you can't measure a curved line. Think of the instruments, all with straight edges. So geometry is naturally associated with straight lines. In India, it was the other way around. It is naturally associated with curved lines. Of course, there are straight lines too. But you can't do it. See, you use a protractor to measure angles. How do you construct a protractor? So it takes a semicircle, divides it into 180 equal parts. But what's the definition of two curved lines being equal in length? You need something to measure a curved line. It's not provided. You're indoctrinated into using it. Just use it and don't think about it. That's what's called being uncritical. That's what's called being indoctrinated. So how do you divide? Empirically you can do it. But they tell you formal math is not empirical. Has to be non-empirical. Has to be metaphysical. Try doing it. But here you can't even do it empirically. Okay, so that's a challenge. If somebody wants to take it up, you're most welcome. So why, this is one of the problems that I had as a kid. Oh, maybe I got it wrong because my protractor is the wrong size. Why doesn't the size of a protractor matter? Because it's a property related to a circle. You cannot understand it in the context of triangles. Alright. So in India you had the Shulba Sutra. What's the Shulb? Shulb is a flexible string. With a flexible string you can measure curved lines. You can measure angles. An angle is the length of a curved arc. You can measure it empirically, you are doing it empirically. And there is a difference of philosophy. What's the difference? You accept. Now if you take the Upper Shulba Sutra, it is Sanitya Sa Anitya. Anitya, non-eternal. This knowledge is non-eternal. And imperfect, Sa with Shesh, Avashesh, with some remainder. So that's there in the Katya and Shulba Sutra. So you are doing something which is non-eternal knowledge with some remainder, it has practical value. It's not perfect, it's not eternal knowledge, and that's the fundamental basis on which the calculus was misunderstood in Europe. So it's a delusion to say it is superior, perfect, eternal, infallible. Anybody who makes these claims about perfection, eternal knowledge, how do you know the knowledge is eternal? We live for a very short period of time. And anybody who claims he has eternal knowledge is obviously going too far beyond himself. Anybody who claims it's infallible, I make mistakes all the time, I'm sure all of you do. So we are all fallible. So to claim infallibility is something wrong. And you should suspect it. Anybody who claims perfection, see, we are all imperfect. How do you claim perfection? So anybody who makes these kinds of claims, there is something wrong. You should suspect it. And that's the point that I would like to drive home, that it's a delusion, it's a religious delusion. I'll come to what is happening. Let me go to the Aryabhata's value of pi. There also he uses the word asanna. So this is asanno. Okay, so it's a near measure. So he's giving it accurate to 5 decimal places. And he's mentioning it's the length of a curved line, it's the circumference of a circle whose diameter is 20,000. And of course this value of pi is repeated, just remember this point, it's repeated by Simon Stevin, who was a navigational theorist in Europe in the 16th century, who gave the decimal fractions and so on, same Simon Stevin. Now this is one of the reasons why I'm really happy to be here, and I told Sam Petroda. So we had a discussion when he was chairman of the Knowledge Commission. And I said, why don't you teach things like this? He said, no, we are not going to do it. If you are doing trigonometry, you should teach it the MIT MOOC way. And that uses triangles. And so my point was that what you learn, if you have not cross-checked it yourself, it's not your knowledge. It's somebody else's knowledge which you are repeating. And we cannot do that with knowledge. You can do that with a company. You don't want to reinvent the wheel. But with knowledge, you have to check and cross-check every little bit. And then everything changes. So, using triangles, not the right way to do geometry, to do trigonometry. And my son now is sitting here, who is now a professor in Harvard, visiting professor. He asked me this question when he was in 8th standard, what is sine of 1 degree? How do you calculate it? You cannot do it geometrically. Geometry only works in conditions of high symmetry. So you have to do it numerically, the way Aryabhata did it. Okay, so this is the table you learn, and this is the table which Aryabhata discarded. Just think of it, you are 1500 years behind the times. So, this is the table which he discarded and went ahead because he gave a table of 24 values. So you need numerical methods to calculate, and you still need numerical methods to calculate. You may use a calculator, whether or not you understand what process it is using, or a computer or whatever, but you still need numerical methods. You still do it the way Aryabhata did it. You do not do it the way of triangles. It's impossible. My software called Code, maybe I'll exhibit it, I use it sometimes. So it solves ordinary differential equations. I'll show it to you maybe later if somebody is interested. So this was a striking shift that Aryabhata did. This is where the calculus originates. That he is talking about difference equations. He's using difference equations to calculate the value of sine. And he's not using geometry. Alright? And difference equations are only metaphysically different from differential equations. If somebody tells you to the contrary, don't believe. Because all practical applications are still done with difference equations. If NASA wants to send a rocket somewhere, they use difference equations. Right? To simplify, if our ISRO wants to send a rocket to Mars, they use difference equations to calculate the trajectories. So he solved these equations using linear interpolation, what is called rule of 3, which you must have studied in primary school. And it's today wrongly called Euler's method. Euler, of course, studied Indian texts. He wrote on the Indian calendar around 1700, but he did not acknowledge it. Those were the days of the Inquisition. They never acknowledged any non-Christian sources. This was, acknowledgement meant, well, death by torture, so nobody was going to do it. So now I will skip over this. Main point I want to emphasize is that in Ganit then, Aryabhata does not state the sine values proper. He states the sine differences, which are later called khandaja, 3.75 degrees apart, because the differences are what you need for interpolation. I want to calculate sine of 1 degree, so I have to interpolate. And for that interpolation, I am going to use the difference. Or, well, I can sum up the differences to calculate at the end points. So I only need the differences. So this is what he says. Now this I am sure no Sanskritist will understand very quickly. It's only the last word which is Sanskrit. The rest is all Aryabhata's numerical notation. And so I think we can kaladhajya. So he is giving the ardhajya in kalas, that is minutes. Okay, so that's the idea. So I will skip over this. What is this numerical notation? Somebody wants, I'll come back to it. It's a very compact, very good system, but very difficult to pronounce. So nobody used it. So this is the translation. And what you have is, you have the circumference of the circle in minutes. So not in 360 degrees, but you have a higher order of accuracy, 2 minutes, which is what Aryabhata is using. And he's giving I'm just calling it R sine, differences. Alright, so the rest of it is, he just states that, and that's the sine difference in minutes. Now the method by which this was calculated, I want to point out that it's a difference equation. So this is the corresponding stroke in Ganit 12, and maybe if I give it to you in terms of the formula, what he is doing may look simpler. This is his formula. It's corrected later by Nilakantha in the 15th century because Nilakantha is working to the accuracy of thirds. Aryabhata is working to the accuracy of minutes. So he is alright with this formula, the corrected version by Nilakantha. But the point is second differences. You see, these R's are sine differences, and then you have a second difference which is brought in, and the second difference is also used by Brahmagupta, who goes back to the old table which you study in school, 15 degrees apart. He says this Aryabhata doesn't understand I know, and you can use quadratic interpolation to get the same accuracy. So that's his point, but he is wrong in that. And this is the thing I want to stress, that what he did cannot be understood as an algebraic equation. Just cannot be understood. So you can calculate the differences, but if you try to calculate, what you want to do is calculate the sign differences, not the second differences. Then you would get wrong values if you just used it as an algebraic equation. All values would be wrong. Okay, so there is never nothing which is a multiple of that, and so it cannot be used as an algebraic equation. Okay, you are doing it recursively, you are doing it, it is like Euler's method, it is Euler's method, a so-called Euler's method. Euler got it from India, he studied Indian texts, as I already mentioned. Now let's look at the other part of it, which brings us to the conceptual issue involved. The algorithm or whatever process he has got is a non-terminating process. You know other such things, for example, square root of 2. So square root of 2, if you try to calculate, the process is not terminating. Now what do you do in such a case? And you know it has to be non-terminating because you know that the decimal expansion, if you like, for square root of 2 is not going to terminate, right? That's an infinite series. So non-terminating process is an infinite series, and that is what you have got. And so those sign values developed gradually over 1,000 years. There was accuracy to the second by Vateshwar in the 10th century. To the thirds, it was attempted in the 9th century by Govindaswamy, he got one value wrong. And it was achieved by Madhav in the 14th century. There is a technical issue about the kind of series, Vara Sankalita, which has to be summed. I won't go into those details. Basically, they extended Aryabhata's process. It's not Kerala school. It is Aryabhata school in Kerala. Let's be clear about that. They call themselves Aryabhata, disciples of Aryabhata. And some people are also trying to push Aryabhata from Patna into Kerala. That's not true. Aryabhata was a lower caste person from Patna. The name indicates it's Bhatta, not Bhatta. And his disciples were the highest caste Nambudiri Brahmins from Kerala. Like Nilakantha Soma Supram, so he performs the Soma sacrifice. He's a very high caste Brahmin. So there was this gradual progress. And you can see that also in other people. 7th century Bhaskar, one's figure is that. Vateshwar's figure has gone to seconds. This is in minutes, and then it's in thirds. Devo Vishwasthali Bhrigu. This is reverse hexadecimal Katapayadi system. Too complicated to explain the technicalities. This is another value which you find with Madhav for pi, which is now correct to 12 decimal places. So that's what it says. Madhav or Sangam Gram gave this number, which corresponds to this, and it's only these two values which are, well, it's correct to 11 decimal places, 12th and 13th are little wrong. So it's very highly precise. And not only is this so highly precise, you also have correspondingly very, very precise sign values. So how precise? So this is how they are stated, by the way. Somebody was asking the other day, how do you separate science and culture? So you don't. This is a poem, right? It's a table. You would write it like this today. So this looks very nice, and you can try to make some sense out of it. So this is the Katapayadi system, Katapaya Adi. So it's based on the alphabet. And this is minutes, seconds, thirds. So this is an idea, and just to give you an idea of how accurate it is, these are the sign values. So you can look at the accuracy of the table. It's extremely precise. And if you were just to use a simple Taylor expansion, you know it's not going to be so easy to get that kind of precision across the entire quadrant. But he gets that. So there are techniques which are done to do that. The point is, why was so much precision needed? Now this question needs to be asked, and it was needed for astronomical models because they kept going wrong and they kept trying to make more and more and more precise computations. And it was needed for the two key means of wealth. And the two key means of wealth were overseas trade, which needed good navigation, and agriculture. Agriculture, which needs a good calendar to tell the rainy season. And I have another talk and a video which should be put up, a number of papers on this. The Gregorian calendar is a bad calendar, it's an unscientific calendar, it doesn't tell the rainy season, it ruins our economic interests. And nobody does something. Well, I've been complaining about it for the last 10 years. But people just don't pay attention. Each year there's so many, millions of dollars spent because of anticipated drought. So once again, I won't go into the details since everything is available. The video will be put up shortly. The paper is there. The presentation is there. You can take a look at that. So for the method, let me focus on navigation because that was the issue which was required for transmission. So you need to determine local latitude. See, even for the calendar, you have to calibrate it for the local latitude. There was a meridian of Ujjaini, and there was on which the meridian of Greenwich is copied from. That's the idea. So there was this local latitude which you need to determine even to calibrate the calendar for the local place. India is a big country. So you could determine it from the shadow of a new moon that's there in the Laghu Bhaskari, or measurement of solar altitude at noon, which also needs a good calendar because you want to know the precise date of the equinox. It was not possible on the Gregorian calendar. Well, there was no Gregorian calendar then. It was only a Julian calendar. And that didn't have the right date of the equinox. That was the substance of the Gregorian reform. You also needed to determine the size of the earth. Please note this carefully. This is an important point to which I'll come back. And you find the size of the earth mentioned in all these books in Jojans. We don't know what is a Jojan, but we do know Al-Biruni's estimates, which is stated in Arabic meals. We know that's very accurate. The accuracy is to within about 0.4% or something. And that is what Khalifa al-Mamun also did, but these were all done sitting at home or while climbing a mountain. And they could solve longitude triangles, where this thing enters as a parameter, using latitude differences and departures, and this is there in the Mahabhaskari. So now let's look at European navigational knowledge. So Columbus and Vasco were navigationally challenged. Alright, they came to India for trade, they were poor, we know that. And they were navigationally challenged. Why? I'm just giving an example. There are more details in my book, Cultural Foundations of Mathematics. Columbus mistook Cuba for China. He did that twice. And then he wrote in his thing, the instrument is broken. How can the instrument be broken? It has only one moving part, which is a plumb line. No? So how can it be broken if it is broken? You can see it, how you make measurements at it. And Vasco da Gama, he had an Indian navigator. He couldn't come across. So he had an Indian navigator, Kanak, and to bring him from Melinde to Africa, and he observed carefully what was the instrument that this navigator was using. It's called the Kamal or the Rapalagar. So they use a peculiar language called Arabic Malayalam. So he said the pilot was telling the distance by his teeth. Now if you want to know the inside story, the pilot was using pole star. The word for the pole star in Malayalam is cow. It's also the word for teeth. And the instrument has a string which is held between the teeth when you make a measurement. You measure the altitude of the pole star by holding it like that. So I have a whole chapter on it in my book. I won't get into that because my point today is something slightly different. Okay, the Jesuits set up a college because they follow this kind of a translation. The Toledo translations were extremely successful in bringing Arabic knowledge to Europe. It was not Arabic knowledge, it was knowledge from all over the world as it is in any library. But it was in Arabic books. And so they did the same thing in Cochin. And instead of the Mozarabs and the Jews, they had the Syrian Christians as intermediaries, so they had all the local knowledge. In fact, their college used to teach Malayalam to the local Syrian Christians. Now when they imported it, they were able to solve the latitude problem and the loxodrome problem. I hope you understand what's the loxodrome problem, because straight lines were used. Now if you follow a straight line course with a compass, or with a stellar rhumb line, you take two stars, see the line joining them, straight line joining them, and follow that course. You won't follow a straight line path because the surface of the earth is curved. Escher has some drawing on it as well. It will, except in cardinal directions, you will go wrong and end up at the pole. So this was the problem of curved lines. Loxodrome means curved lines. You're setting a straight line course, but you're traveling in a curved line. How do you solve it? You solve it with the Mercator's chart. It's a common map of the world, which all of you have seen. And why is Greenland so big and India so small and so on? That's not something which is done deliberately. It comes out because they want straight lines. If you set a course in a straight line, you should get a straight line. That requires very accurate trigonometric values, table of seconds. And Stevin's table was not up to the mark using Aryabhata's values. And what was Mercator's source? We don't know because he was arrested by the Inquisition. Obviously his source is a secret. We know that his map projection, as Needham will tell you, was from China, but the trigonometric values were from India. So it also used the length of the tropical year because that was a very important input. The Gregorian calendar reform had to be carried out for purposes of navigation. Why was it carried out then? Why not earlier? Why not later? Because after all, the error had been piling up for 1,000 years. People knew there was an error. So it was carried out then because it became very important. And the point I am making here is that it was not understood in Europe. Newton didn't accept it. Because the Protestants said it's a papal plot. They accepted it only, Britain accepted it in 1752. And Russia accepted it in 1970, 1980. So this is the person who did the calendar reform was Clavius. He was a Jesuit general. His student was Matteo Ricci, who was trained in these methods of arithmetic, of navigation, sent to India. And this is his handwritten letter from 1580. So as you see here, he is talking about Muro Honorado. So Honorable Moor or Brahmani intelligence, so that's intelligent Brahmin. So he is looking for the methods of measuring Indian timekeeping. He is in Cochin doing that. Before he goes to China, he is famous for going to China, but he was in Cochin. This is his handwritten letter. So now comes to the part about misunderstanding. This transmission was done, it was done for the purpose of navigation, it partly solved the navigational problem, were able to determine latitude, were able to determine loxodromes, but failed on the problem of longitude. Why did they fail on the problem of longitude? Because they could not get the size of the earth right. Columbus underestimated it by 40%. Obviously he had a vested interest. He wanted to raise money for his project. So one understands. But Clavius published Mather's table in his name with interpolations in 1608. Uses the same values. But now such precise values, he should know trigonometry. If he knows some trigonometry, he should be able to calculate the size of the earth. But he didn't know that. The size of the earth was done only by Picard in 1672 in Europe, and even then people didn't believe it. Because the carrying of globes was banned aboard ships by Portuguese law. It led to so many navigational disasters. But the point is, it's something very simple. Any child can do it. But they could not do it. Therefore, there was a longitude problem. Now you see, let us say, Dava Sobel's book on longitude glorifies the development of the chronometer. But the problem is here. This is not talked about. Why didn't others have a longitude problem? Why did only Europe have a longitude problem? Because they could not measure the size of the earth accurately. And now here are my students for the History, Philosophy of Science course. It's in Al-Bukhari University. I took them on a trip to measure the size of the earth just to explain how easy it is. So you go in equinox and you measure the angle of the dip of the sun, and you can measure angles very accurately using a watch. So they did that, and they arrived at the size of the earth. So the point is, Europeans were not able to do this simple thing. And therefore they had a longitude problem. Therefore the longitude problem persisted until the 18th century. Many governments offered huge prizes. Starting from Pedro Nuno's, the Spanish prize, Portuguese prize, Spanish prize, Dutch prize, French prize, British prize. 1711 by the Board of Bonney. So until 18th century, Europeans were not able to navigate correctly. They used dead reckoning, which reckoned with many people dead, and that was a problem which they were trying to correct. So I hope you know what is dead reckoning. You call log table. So they used to throw a log overboard, and they used to see, then they used to pull it in and try to measure, and they used to tabulate that. So that's where this idea comes in. So now let me come to the question of the next level of misunderstanding, which happens with the infinite series. You saw what happened in the case of navigation. They got the knowledge, but they got part of the knowledge. They could not calculate the size of the earth, and therefore there was a longitude problem which persisted for so long. And it was the major scientific challenge. All your academies were set up mainly to solve that problem, because that was the key source of wealth, anticipated source of wealth. Now this is what happened again with infinite series. That the methods, Indian methods of summing the series were not understood in Europe. So finite geometric series was known since the Yajurveda. You know, if you have 1, 10, 100 and so on, that's a geometric series. It's just exhibited. There were methods of summing it. They are given in all these texts, in Aryabhata, in any of the texts you take, Mahavir or Sridhar or whatever. Infinite geometric series had appeared in India by the 14th, 15th series of 15th century. And you find that, for example, in Nilakantha's Aryabhata Bhashya, his commentary on Ganit 70, and that's the text, and that's the statement. It's done slightly differently because you have a divisor, instead of you do it by looking at common multiplicator. Here he is looking at a common divisor. So a slight difference of expression, but the effect is the same. And the sum value is the same. So that's an infinite series because there is no other remainder term which has gone off. And this number pi, like the number square root of 2, requires an infinite series. You cannot represent it in any other way. So one such series which was credited wrongly to Leibniz is found in the 16th century Yukti Deepika. This is it. And again it's about the circumference of the circle. So you, to the diameter multiplied by 4, alternately add and subtract the diameter multiplied by 4 and divided by the numbers 1, 3, 5, etc. odd numbers. So this is the series. Cancel out 4D and that tells you that's the form in which you look at it today. That's the Leibniz series, so called. As Newton said, Leibniz didn't understand it. He was right. Newton didn't understand his series either, which was the sine series attributed to Mars. And it baffled all Western thinkers, Descartes, Galileo, Newton, Berkeley. A big quarrel about it which went on. What's the right way of summing infinite series? So let's take a look at what Descartes did. So Descartes says in his geometry, the ratios of curved and straight lines are beyond the capacity of the human mind. See, curved lines are not trivial. Beyond the human mind, according to this great geometric thinker. So this is what he says. And of course you can build an apologia for it, but that's not the point, that's what he says literally. And that ratio, because Fermat and Pascal were recipients of these texts, and they took, Fermat's challenge problem is a solved exercise in Pascal. No European was able to solve it for almost a century. So this is the difference, that in India, in the text, you had, it was called Raju, you are taught to measure a curved line with a flexible string. And so once you do that, you can always straighten it and compare it to the straight line, with the length of a straight line. It's a very simple process, it's done empirically, alright? And just to remind you, you can't do that with the geometry box which you have in school. The point I am making here is that just as, whether in terms of navigation or whatever, we need to critically examine. I am not saying that you should reject something because it's Western in origin. You have to take care of your self-interest. So you critically examine something. If it is of value to you, accept it. If it is not of value to you, reject it. And that has not happened. There has been no critical application of the mind. Everything has been accepted in toto. That's not the right thing to do. So you accepted the misunderstanding, went off there and came back with a misunderstood form in colonial times. It was blindly accepted. It continues to be accepted. That's the problem. People refuse to debate it. They will abuse, they will do everything. Ape the West, that's their point. Don't make a critical evaluation because you're not capable of it. That's something very wrong. So you could take a look at it, Indian rope trick. So now the point is, what do you need that perfection, those limits for? For most practical purposes, most of you would use 3.14 is a good thing, 3.14, 159 is a good thing. That's my phone number, by the way. So you could do that. And if you wanted to, you can go to 1,000 places, billion places, as many places as you want for the particular application at hand. You want to send a rocket to the moon, you don't want to have so many decimal places. 32 would be alright. If you want to calculate some circular error, probably. 32, 64, whatever you like. You have 64-bit architecture now. The problem is, that is still practical value. Understood? But here, Descartes wanted the perfect sum of an infinite series. I am taking a charitable interpretation. Okay. I think that that's the way to argue. You have to give the most charitable interpretation of the opponent against whom you are arguing. So this is what I am saying, that you wanted the perfect sum which leaves nothing out. Not billion places, not trillion places, not zillion places. Perfection. So how does he get perfection? He thought you have to physically sum everything term by term. And if you do that, that's a super task. It will take an infinity of time, an eternity of time. And therefore it cannot be done, only God can do it. Therefore it's beyond human minds. That was his thinking. Galileo concurred in his letters to Cavalieri, who was one of the founders of the calculus. He waited for Galileo. He said, I don't want this disreputable stuff. Take it away, take it away. That was the situation in the 1630s. But the point you have to ask is, why is math perfect knowledge? Use it for practical applications, use it for engineering, use it in physics by all means, but why do you want perfection? You don't want perfection anywhere there. Why is it eternal knowledge? And this is the problem. So why can't we work with just useful knowledge which is imperfect and non-eternal, as in the case of the Shulba Sutra? That's what you do all the time. But you reject the practice. You reject the practice, that's the way people understand. They reject the practice and say, no, this stuff must be correct. Why? So it's a long history. I've written about it quite a bit. So Plato says in Meno, that famous dialogue, Socrates and the slave boy. So Socrates questions the slave boy and elicits his innate knowledge of mathematics. And therefore he claims he has proved the existence of the soul. Please do read Meno. It's available online. Please do take a look at it. He claims he has proved the existence of the soul and its past lives. Because this innate knowledge is eternal knowledge in the soul which comes from past lives. And that's the same thing confirmed by Proclu, who's writing about 800 to 900 years later. So he says mathematics, the word derives from mathesis. What is mathesis? Learning. Learning means recollection of the soul, recollecting its eternal knowledge. That's the meaning of learning. And he says that if you do that, that arouses the soul, makes you virtuous, leads to the blessed life. That's why Plato prescribes the teaching of mathematics along with music. Makes you virtuous, not because of its practical value. So why does it arouse the soul? Because it has eternal knowledge, like arouses like, soul is eternal, this knowledge is eternal, therefore mathematics arouses it. And that's why Socrates uses mathematics and not geography or the latest political gossip. That doesn't arouse the soul. That's the idea. But these are religious beliefs. I may sympathize with them, but they are not universal and they are not compelling. And the point is, why should it come into mathematics? Maybe those religious beliefs I would accept. Supposing I even do, why should it link up with mathematics? That's the problem. And we talk of secularism. Why can't we have secularism in the classroom? Why do we want these kinds of beliefs to be superimposed on the minds of children? So that's one of my petitions to the government, that you teach religiously neutral mathematics. We don't want this talk of perfection and perfect knowledge and so on. There are many other religious aspects of it. If you look at what Aquinas said in Summa Theologica, he said God rules the world with eternal laws. And those laws, eternal laws, are written in the eternal language of mathematics. That's why you write your equations of physics like that. And as I have argued, this is just a superstition, everyday belief. You think the future comes about through your actions. Don't you? A car is coming down the street, you start calculating what is the Newton's laws. Just move out of the way. The simple thing is what you should believe in, and not this guy saying he has this knowledge straight from God. I don't know, why should I believe any of that? I believe my experience. So there is a paper on Islam and science, Gale paper on Islam and science, there are two of them, so look at the Gale paper, and if you Google you'll get it, that discusses this issue at some length, because if you look at the issue in Islamic theology it is different. So it compares the two, Islamic rational theology, Aqli Kalam, and Christian rational theology, and sees the difference. So now there is, for example, you are taught that deduction is infallible. Whenever somebody says infallible, don't believe it. It cannot possibly be true. Alright? So why is deduction infallible? Because Aquinas bowdlerized Al-Ghazali and said that logic binds God. You know all about the mind of God. So, yes please? Oh, that's the key. Alright. No, I can't answer your questions now. So, you have to wait till question time. So the point is that logic is not universal. So Buddhist logic of Chatushkoti is not even truth functional. So why should we have two-valued logic as the basis of mathematics? The Jain logic of Syadvad is not two-valued. So either it is cultural truth or If you say that, look, it's a matter of empirical, common sense or empirical experience or whatever, that logic should be two-valued, then that's decided by empirical facts. So if logic is decided by empirical facts and empirical proofs are fallible, then logic itself is fallible. It's more fallible than empirical proofs because it's based on them, right? Or it's cultural truth. So your idea of, the idea of deduction as infallible is just another religious belief. But Newton accepted all of that. So I want to talk well. And he called, as you know, there was a big dispute and there was a charge against Newton. Leibniz made a charge that he had plagiarized. And Newton appointed a committee, as president of the Royal Society, he appointed a committee to look into the charge. And he was the one-man committee who looked at it. He wrote the report and he reviewed the report anonymously. And in that review of the report, anonymous review, this is what he said, that he was a second inventor, why should he get the credit for it? Which is right. His arguments are quite solid. No, he didn't understand, he needed help, he came to me and asked for help. So how could he understand the series named after him? But same thing is true for Newton. And I won't go into the sine series issue, I'll go into because I want to look at the contemporary applications. And he thought, because d by dt comes there in Newton's laws of motion, right? Eternal laws, which are pretty wrong now for a century, that he wanted to define it perfectly. How do you define d by dt perfectly? So he thought that the perfect way to do it, because it requires the properties of time. Suppose time is discrete. Suppose time moves about irregularly. Those are all the thoughts in his mind. How do you measure equal intervals of time? You can't measure it by any natural clock because something is wrong. He said, never mind. It's there in the mind of God. It's a very convenient escape route. So if you remember what he said in his Principia, absolute, true, mathematical time flows on regardless of anything external, pure metaphysics. But it's there in God's mind and that's all right. So their time flows all right and therefore this is what he did. But the other part of the story is that Newtonian physics failed just because he did not define a proper clock. He said it's okay if God knows it, but if you are a physicist, you also have to know it. You also have to have a clock. You didn't have a proper clock, and that's the precise reason why Newtonian physics failed. Not because of any experiment, because of conceptual confusion about the notion of time. So that's there in my book, On Time Towards a Consistent Theory. Read it long back. The connection now is that the confusion arose because of a misunderstanding of calculus. Now Newton talked of fluxions, no? Things flowing, time is flowing, fluxions, and they have been abandoned today. But how can time flow? This is also there in Sriharsh, Mercator's paradox. Time cannot flow. Something can flow in time perhaps, but time itself cannot flow because if it was flow, there would have to be a second time within which it flows and so on. But the belief persists that you must make time metaphysical, time must be like the real line in order to differentiate, write down d by dt. So limits must exist, you must have a complete metric space, etc. Now that belief is taught to you. Now I want to know, you are here in MIT, just a question, how many of you learned the real number system? You learned the real number system. You are a mathematician?
No, but I don't believe in real number system. I'm a constructivist.
You are a constructivist. So you learned the real, you are a mathematical philosopher of mathematics. Okay, anybody, you did d by dt, right, all of you? How to define a derivative? Come on, don't tell me that nobody here knows how to define a derivative. So, it is not taught except to math majors, as far as I know. So, Shankar, you did a course on calculus in Harvard. They didn't teach you real number system. They taught you about it, they didn't teach it to you. Okay? So they didn't teach it to you. So the point is that you can get along perfectly well without it. That's why they don't teach you. But they say that's the real thing, and that's a problem. For any practical application that you do, any engineering application, any application to physics, any application to social sciences, economics, anything you like, you will never use it. What you will do is you will solve a differential equation numerically. And that's the Aryabhata way. And today you will do it on computers. Computers use floating point numbers which are quite different from real numbers. They cannot use it. It's infinity, it's metaphysics. Computers can't do that. They operate in a physical world. And it's a completely different arithmetic because even the associative law fails for floating point numbers. So what I want to say is that it is calculus with limits is not needed for any practical value, but it's also not sufficient, it's not adequate. And this is a bit advanced stuff. I don't know that discontinuous functions you cannot differentiate. But you need to differentiate them in physics. Shock waves, for example, shock waves, fracture, anybody doing material science or whatever, you have to do that. Right? And they have been used. You must have heard the story of Heaviside. People used it from long before the formalization of real numbers, which took place with the formalization of set theory in 1935. And today you do it using Schwartz distributions, and that's not good enough for physics because the equations of physics are nonlinear differential equations, and so you can differentiate but you can't multiply them. The same kind of problem arises in quantum field theory, in the renormalization. So basically this corresponds to the idea that you need to sum a divergent series. So for example, if I have a series like this, 1 minus 1 plus 1, the sum turns out to be half. Why half? Well, we can discuss it. So the idea is that this is something which has to be done empirically. It's an adjunct physical theory. So as an adjunct physical theory, I can test it out, I can derive some shock wave conditions based on that. I cannot do it in non-empirical. Okay. Or for example, 1 plus 2 plus 3 plus 4, what's your guess? What's the sum, infinite sum? Except for field theorists, except for string theorists, I don't think anybody can give an answer to this. So the answer which was given by Ramanujan and which is used in string theory today is minus 1 by 12. Now figure that out. So the point is, there is no intrinsic definition of these things. You define them as you like, you use them as so long as they are useful, you use it whichever way you like. So today they are handled using non-standard analysis, but you also need empirical inputs. You can't do without empirical inputs. This is argued in my cultural foundations of mathematics. I won't go into that right now. The point I want to talk about is that the key feature you need is non-Archimedean arithmetic. It has nothing to do with Archimedes, but that's the name given, just as the division algorithm has nothing to do with Euclid. It's called Euclid division algorithm. So, key point is that unlike the real number system, you have infinities and infinitesimals with non-Archimedean arithmetic. And that's all that you need. But you have to discard infinitesimals, your limits are not unique. And well, it corresponds to limits by order counting when the formal limit exists. Order counting, so if I have, let us say, x squared by x or x by x squared, you know that as x goes to infinity, that will go to 0. It needs a new philosophy which I have called zeroism based on Shunyavad. It's not formalism. I don't think I'll discuss it right now because I want to finish this off. So this was what was used in Indian arithmetic. It started with Brahmagupta, who used the term avyakt numbers for polynomials. And once you have an avyakt number like 3x plus 2, which acquires a value only when you give a value to x, you also get ratios of them, so you get avyakt fractions. Those avyakt fractions are rational functions called today rational functions, and very formally they constitute a non-Archimedean ordered field. And therefore you have to discard infinitesimals in order to get limits in this field. You could perfectly well work with this number system. The point about zeroism is that it works with numbers systems which are larger than R and also smaller than R, like floating point numbers. You can apply it with computers, you can apply it here theoretically. Well, this is the method that is essentially used to accelerate the convergence of this floating convergence series. So that's there in my book, Cultural Foundations of Mathematics, and I can only show you a picture. I can't carry the physical book, so I hope it is there in your library. The point is that if you make these changes, if you correct Newton's conceptual error, that leads to a paradigm shift in physics. It leads to a new theory of gravitation, which I have called retarded gravitation theory. It leads to modified electrodynamics. All this is explained in a series of articles, expository articles in physics education in India. They are all available online, and it's a continuing series and still completed. The other thing with those who don't want to define a derivative, you didn't do it because you found math difficult. Am I right? The question is, why is math difficult? Look at what Plato is saying. Math is like music, arouses the soul. Most of you would like music, I'm sure. So music is still likable. What happened to mathematics? Between Plato and now, what did we do to it that it has become such a nightmare for people? We still keep talking about the aesthetic value of mathematics when people are finding it so nightmare they give it up. So there is a problem there on the principle that phylogeny is ontogeny. We teach it the way it was misunderstood in Europe, we should teach it the way it actually developed in India. And that's what I did. And with great success, because it becomes extremely easy. The SPAC calculus text with 1300 pages, big size, small print, and with an accompanying CD, DVD. You can do all that in 5 days. So I have demonstrated this with 8 groups in 5 universities, all kinds of groups, postgraduate mathematics students, undergraduate applied math students, undergraduate pure math students, non-math students, and even monks. But no education at all on that. Some of them, they could not even, they failed actually, but the rest of them who could multiply, who could do basic arithmetic, they succeeded. So this is the group of people from Sarnath, Central University of Tibetan Studies, and half of them passed, half of them failed, plunked. The idea was that after 5 days you should be able to do a problem drawn at random from one of those SPAC calculus texts. Not a problem, set of problems drawn at random. This is the group in Tehran, and this is the group in Delhi, Ambedkar University. As you can see, they are smiling because they all passed. They were very happy, extremely happy that they could get over because they had this great sense of inferiority not being able to do mathematics. They were extremely happy. So this is the big picture that I would like to give you to conclude. That whole lot of basic school maths, I didn't cover probability, but I also have an article on that, probability in ancient India. The story is similar. Kolmogorov probabilities don't work. Don't work with the law of large numbers. I didn't talk about it. So most of this, arithmetic, trigonometry, calculus, and probability, it developed in India. So you find probability and dice game mentioned in the Big Ved and in Mahabharata. Statistics, how to count the number of things in a tree, number of fruits in a tree. We're using sampling. So this math was misunderstood in Europe, and that inferior understanding was given back as superior and globalized during colonialism. We have never examined it critically, and we ought to do that. That's the point. It's still taught today, and we know that there are so many claims of superiority that were made. Colonial superiority was preceded by claims of racist superiority and claims of Christian superiority, as in the US Supreme Court judgment that the native Indians in America lost their right to land after being discovered. There's a doctrine of Christian discovery which is part of Supreme Court judgment. It is listed in my book. You can take a look at it. So the idea that formalism is rigorous, superior is wrong, and it has a religious basis. The time has come to be critical and discard it. What do you do math for? You want to do commercial problems, you want to do physics problems, you want to do engineering problems? Yes. You want to do aesthetics, put it in the aesthetics department, keep it away, let them do what they want to do, because nobody else understands the aesthetics. So you want to go back to our roots and do that, and these are some of the references. They are posted there, and there's a longer reading list there. Thank you very much. I hope I didn't take too much time.